Hey student, welcome back. So I'm very excited for today's video because we're going to be moving on to differentiation or derivatives, which a more interesting part of calculus. We started with limits to sort of find our footing and get ready to summit the mountain of differentiation. Sometimes calculus is compared to two mountains, one of derivatives and one of integrals. And limits are sort of our snowshoes or our training in order to climb those mountains. So now that we're ready, we can start to talk about derivatives. Before we get into derivatives, I'm going to look at three different terms: the derivative, the slope of the tangent line, and the instantaneous rate of change. All three of these things are the derivative. They're the same idea: the slope of the tangent line, instantaneous rate of change, and the derivative. We're going to be talking about all three of those, and they're all really the same thing. Okay, so we're going to define the derivative today. So here we've got a graph of a function f of x. And in our first video, we were actually kind of talking about this concept, right? If we were to find the slope of this graph over 2 points, maybe from here to this point, we would say if this was point B, for example, this would be f of b. This would be f of x. And the slope of the line between these 2 points, we'd call this the secant line because it touches in 2 points. Slope of this line would be f of b minus f of x all over b minus x. Okay. And we talked about bringing b really close to x and actually making it the same. We couldn't do that because we get 0 over 0. However, now that we know what limits are, we can start to think about this a little bit differently. So let's get rid of this. And let's say, instead of b, let's pick an arbitrary point here. And instead of talking about just some point b, let's say the distance between these 2 points is h. So we're going from x to a new point, x plus h. So our x value would be x plus h here. And our y value would be f of x plus h. We've got our 2 points, f of x plus h. If we were to connect them with a line like this, another secant line, we could find the slope by saying f of x plus h minus f of x all over x plus h minus x. Okay, and then we can kind of combine like terms in the denominator. We have f of x plus h minus f of x all over h. Okay, so this is still an average rate of change, or the slope of a secant line. It's not yet the derivative. In order to get the derivative, we need to bring this point, that x plus h point, we need to bring it much closer to our x value. So if we do that, if we keep bringing it closer, what we're doing to h is we're making h very small. We're taking the limit as h goes to 0. If we do that, we will get a much better representation of our slope at that exact point x. And this is the definition of the derivative. The limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, we're going to be working with this definition in order to actually find the derivative of a function. Okay, so here below, our function is x squared, f of x equals x squared. So if we want to find the equation for the derivative at any point on this graph, we're going to plug into that formula that we had above. So that was the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so the limit as h goes to 0. Plugging in x plus h, remember this is sort of a composite function, right? Where we're plugging in x plus h into x squared. So we need to be conscious of that this is x plus h all squared minus x squared over h. Okay. Now we can expand. I'm going to, as h goes to 0. And I know it's annoying to write the limit every time, but this is what we've got to do. We've got to do it. All right, so now we have x squared plus 2xh plus h squared minus x squared all over h. We can cancel. We have an x squared and a minus x squared. And then you'll see, well, let me go ahead and write it again. So the limit as h goes to 0, 2xh plus h squared all over h. Now we can cancel some h's. So we can cancel this h with this h, and then 1 from the h squared. Okay, so finally, we have the limit as h goes to 0 of 2x plus h. Now, if you remember your limit laws, you know that we can now just plug in 0 for h. And so our derivative, which we'll talk about the notation a little bit later, we call f prime of x. That's how we denote a derivative. One way that we denote a derivative is 2x. The derivative of this function, x squared, is 2x. Now, that is not the slope at any particular point, but we can plug in any point that we want to find the slope. So if we wanted to find the slope at x equals 2, for example, so here we are at 2. If we wanted to know the slope of this tangent line, we'd say f prime of 2, that would be 2 times 2 is 4. So the slope of the line that touches just at 2, 4, that's the point that we're at, 2, 4, the slope of that line is 4. Okay, now let me go ahead and draw that. There we go. Something like this. Okay, so here's our tangent line. And I mentioned secant line earlier. The difference between a tangent line and a secant line is that a secant line touches in 2 places, where the tangent line touches in only a single place. Only at that point that we want to know the derivative, or the instantaneous rate of change. Now we're going to be looking at a second definition of the derivative, and it's going to give us just the slope at the value we're choosing. Here we're looking at a point A, and we can pick an x value, x, and find the slope once again. And so f of x minus f of a all over x minus a. And once again, we have an average rate of change. However, if we bring this x value closer to a, then we'll end up getting the slope of the tangent line. So in order to get the second definition of the derivative, we'll take the limit as x goes to a of f of x minus f of a over x minus a. And this will give us the derivative at a specific point a. What do I mean by that? We already know that the derivative at x equals 2 is 4, but using this definition, we can solve for it algebraically. So the limit as x goes to 2, that's where we're looking for the derivative of x squared minus, and we have f of a, that's just plugging 2 into the function. So that would be 4, 2 squared is 4, over x minus 2. Just following from the definition. So to simplify this, we couldn't just plug in. We would get 4 minus 4 is 0 over 2 minus 2 is 0. 0 over 0, we can't solve for that, but we can factor. So the limit as x goes to 2 of x minus 2, x plus 2, over x minus 2. Here we can cancel. The x minus 2's will cancel. So now we just have the limit as x goes to 2 of x plus 2. Once again, with our limit laws, we can just plug 2 directly in, and we do get 4. F, and in this case, I believe we're calling it g prime of 2 is equal to 4. So Today, we saw two different definitions of the derivative of a function and the derivative at a point. And we confirmed that the derivative is the same thing as the slope of the tangent line, which is the same as the instantaneous rate of change. Keep watching, and I'll see you in the next video.